Um, Hi everyone. Yeah, first of all, I want to thank organizers for the opportunity to speak here. So I'll tell today about recent combinatorial proof of Maslov index formula in Heegaard Floer Homology. So I'll start by recalling some basics on Heegaard Floer Homology, and I'll talk about a bit the Maslov index formula, and we'll sketch the proof. So we start with uh, recalling what the Heegaard diagram is. So we have some Riemann surface of genus G, and we assume there is a metric on it, though nothing will really depend on this metric. And then there is a collection of simple closed curves alphas and another such collection beta. So each collection curves do not intersect each other, but we assume that curves from different collections intersect at 90 degrees angles. So we would denote this data as a Heegaard diagram. It's usually called an pointed Heegaard diagram because for the calculations of actual Heegaard Floer homology, people usually at some points in the regions of the complement, but for Maslov index computations, it's not really necessary. So this part of data won't be in this talk. So here's an example of such Heegaard diagram. Here, G is equal to 2 and K is equal to 3. So we have these three red alpha curves and three blue beta curves, and presumably all these at all these intersection points, we see 90-degree angles. Then the generators in the Heegaard Floer complex, well, for any version that you like, are collections of points of intersections between alpha and beta curves. So in this example, for instance, there is the pink collection of points x1, x2, and x3. And for instance, these orange points, y1, y2, and y3. One can think of any such collection as a point of intersection between two real tori in a cave-symmetric product of sigma. And these tori are associated with alpha and beta curves. Okay. Then the differential counts certain J-holomorphic curves, connecting the generators with some boundary. So assume we have this four-dimensional manifold, and we could think of it as of a strip over sigma with some nice, almost complex structure. We pick a cylinder over alpha and cylinder over beta on the boundaries. Then we consider some moduli space of Riemann surfaces with boundary and K negative boundary punctures and K positive boundary punctures. And we then consider first homology classes of maps from such Riemann surfaces to the pair of these four-dimensional manifold and the union of these two cylinders, such that it converges to X near the negative boundary punctures and to Y and near the positive boundary puncture. But by this, I mean for each boundary puncture, there is a point in the collection which develop converge. And we can then pick a class phi in this homology group and associate a moduli space of J-holomorphic curves connecting X to Y. So curves in this class solving some D-bar equation. And then it appears that, well, then we can, the differential counts the number of elements in this moduli space for those y and phi, satisfying that the dimension of this moduli space is equal to 1. And it was shown in the original works by Ozat and Jabbar that it only depends on phi, and it will be called Maslov index, and I would denote it by phi. So now let me tell a bit about Robert Lipshitz's work and how he introduced combinatorial formula to compute this Maslov index, which is quite useful. So first we denote by Ri's regions of a complement in sigma to alpha and beta curves, and we pick a point zeta I in each region Ri. Then we call a coefficient, like a coefficient of class phi at region Ri, to be the intersection number between class phi and the strip over zeta I. And so the claim is that this number really doesn't depend on this choice here. Then for P, which belongs to the intersection of alpha and beta curves. So let's say here we have P, here we have region R1, R2, R3, and R4. Then we define a coefficient of phi at point P as the average of these numbers. So let me write it like this. So it's a sum like this, and we denote by a shadow of phi, so-called projection of phi to sigma, as a two-chain where each region comes in with the coefficient of phi at this region. For any region, we can define its earlier measure by just computing a curvature with respect to that metric that we chosen in the very beginning, and this would assign to two m-gon regions a number like this, and we extend this earlier measure to any shadow d of phi by linearity with respect to such decomposition. And then Robert Lipshitz proved that the Maslov index of class phi can be given by this formula. So one needs to compute the earlier measure of this shadow and coefficients at the endpoints of this class phi, where when we have a collection of points, P like here, so it's x1, etc., xk, we just take a sum of such numbers for each xi. So let me give you a couple examples of computations. So this first region here is called bygone. So for instance, for x, we have only one region covered. So it gives 1/4 here. Same for y, it gives 1/4 here. The earlier measure assigns to this two-gone 1 minus 1/4 for each angle. So it's 1 minus 1/2. And then formula says that the Maslov index would be indeed 1. And this corresponds to our intuition that from a strip to a strip, there is a one parameter family of maps. Okay, slightly more complicated case of rectangles. So here, so here it is point y1, and here it is point x2. So again, for nx, we see just 1/4 and 1/4 for each of these regions. So we get 1/2, same for y, 1/2 here. Other measure would be 0 because we have to subtract from 1/4 4 times, and we again arrive at 1. So for both of these regions, the Maslov index is equal to 1, according to Lipshitz's formula. And in the remaining time, I'll try to sketch the proof. So, but given two generators x and y in some Heegaard diagram, we denote by d of xy the set of all possible shadows of those homology classes phi. So namely, these are the two chains which can be given as a sum of regions, and along alpha curves, they connect x to y, and along beta curves, they connect y to x. So then we can define the so-called combinatorial index of any domain by this formula, and assume we don't have Robert Lipshitz's first. So we may try to prove that the Maslov index is equal to this combinatorial index using some shared properties of both indices. So what are those properties? First, they are both additive. So by this, I mean that, for instance, if there are two domains, one connecting x to y, the other connecting y to z, we can define the so-called joint sum by just taking a sum of chains. Then it was first shown by Sutri-Sarkar that the combinatorial index satisfies the additivity condition, and for Maslov index, on the contrary, it's quite straightforward. It's just a topological property of Maslov index if it's additive, where phi and phi prime again connect x to y and y to z. Okay, and the other property that I'm going to use is the so-called stability, namely that the index is preserved under some transformations of Heegaard diagrams, namely isotopies and empty stabilization. So what are they? Main example of an isotopy is a so-called finger move. So in this picture, we have finger move along alpha curves. So we draw some dashed curve here, and then one can think that we poke a finger along this dashed curve, and this is the picture where we arrive. We move all alpha curves and remain beta curves untouched. The empty stabilization is adding or increasing the genus of surface by one, but making sure that it happens away from a domain. So here is a domain, and here a new handle, and it's at some distance away from the given domain. So then we show the theorem that there exists a unique index from a collection of all. So D here is a collection of all domains over all Heegaard diagrams, and we show that there exists a unique such function from this collection to Z, which satisfies following four properties. So it's additive and stable, as we just discussed, and it's equal to 1 for all bigons and rectangles, and we already saw that it is satisfied by the combinatorial index. Moreover, this index agrees with the combinatorial index, but this is quite straightforward. And for any Whitney disk phi, the Maslov index of phi is equal to the combinatorial index of a shadow of phi. So the proof of this theorem is based on the following so-called decomposition theorem, which states that assume we are given some ugly domain living in some Heegaard diagram, then we can make a certain sequence of transformations of this Heegaard diagram, namely finger moves and empty stabilizations, such that in a new Heegaard diagram, the image of D can be represented as composition of ligand, rectangles, and their negatives. And then the proof of theorem 1 follows. Assume we're given such domain D, we apply, also it's theorem 2. We apply theorem 2 to get some D prime, then we can decompose it into a product, well, into a joint sum of bigons, rectangles, and their negatives. And then by additivity, we have this, and we know all these numbers, whether ones or minus ones, according to properties 3 and 4. So in the remaining time, I'll tell a bit about how one could prove this decomposition theorem. So the strategy for this is to at each step make the domain look nicer. So the first step is assume we start with some domain G such that its boundary not even embedded. So let us try to make it embedded. So for instance, here we assume that x1, y1 is covered k times. So x1, y1 is this arc along curve alpha 1, and say y1, x1 is covered k minus 1 times. So here I assume that this means that if we go from x1 to y1, it is covered k times, and if we go this way, this portion is covered k minus 1 times. Then we apply the following finger move. We pick a point on the curve beta 1 and poke a finger along this green curve. So this is the picture at which we arrive. And most importantly, we have created now a beigen B here, and we can consider a new domain D prime, which is equal to minus B join some D. And now it connects not the collection X to Y, but the collection X with X1 being replaced by Z. And one can see that in this collection, the curve Y1Z is now covered K times, and the curve Z Y1, oh, I'm sorry, K minus 1 times, and this is covered K minus 2 times. So we decrease the number by 1. And nothing changed another curves in this picture. So proceeding in this fashion, we can make sure that the boundary is embedded. Well, next step is to make the boundary connected. So here we are assuming that, for instance, this is one portion of a boundary and this is the other portion of a boundary. And then we make two such finger moves connecting this curve to this curve and this curve to this curve. After this, we've created some rectangle here, a beigen here, and a beigen here. And if we had a domain D here, then we can replace it with D prime being equal to, probably some signs will, well, D prime prime. I'm not sure about all the signs, but it should be minus B1, D prime, and minus B2. Then the boundary of this curve would go like this. It will go here, and will travel all the way through. It will come back here, go this way, and come along. So we reduced the number of connected components, and in this fashion, you can reduce it to 1. Well, I'll probably skip this step, but at this stage, we are making sure that the boundary looks like quadrangle or beigen. And at this stage, one may really see that, well, not see, but like reduce to the case where the domain is some like quadrangle with some genus inside. So that's kind of the final case, how we reduce the genus of something which looks like something else. And in the boundary here is say a rectangle. So a mathematician in California in their free time can grow some palm trees. So that's what we are doing here. So this depicts a handle. Assume this circle is attached to this circle. Then we grow 2 palm trees in the following fashion. So a finger comes here and then comes out here, will intersect in this side, And the same happens on the lower boundary. And in this way, we created one rectangle in blue color, one rectangle in yellow color, and these four bigons. And then we can subtract them, and we will be left with the domain inside of this region, and we can assume that all the Riemannian genus is there. So in this way, we reduced genus by. I guess I'll stop here.
Thank you, Roman. That was a very, very nice talk. Any questions or comments from the audience? I guess no one has any questions. I actually have a question. So, can you go back to the statement of the formula? So I was just confused
the
about
statement of the formula. Okay.
yeah.
Maybe
So
here is fine.
when you say a domain, I mean, you define it here, right? But should I just think of the relative homology class of the polymorphic curve when you project it to the surface?
Yeah. So this is like the projection of a relative. Yeah, indeed. So it's like yeah. So
Okay, so this
if you think in terms of symmetric products, it's just like this projection to the first coordinate. In terms of this cylindrical interpretation, it's indeed a projection to the surface.
okay. So basically, this gives you a completely combinatorial description of just computing the Heegaard Floer homology.
Yeah.
You're just looking at the domains that you're seeing on the surface, you compute the index, and then if it's one, then you just count.
Yeah.
Okay.
And indeed, what are applications of your formula? So do you know some specific situations where it helps?
Well, I mean, for any Heegaard Floer homology computations, you need to know where the index is 1, and maybe sometimes you need to know where an index is 2. But so that's kind of why it's applied everywhere, but why you would need to know when the index is bigger than 2. Well, I'm not sure that there are any applications of that. I mean, usually people just need to know when it's 0, 1, or 2.
Thank you.
Okay, so if there are no more questions, we thank Roman again. Thank you, Roman, for the talk.